Hello everyone, welcome to CSCN 1001 Computer and Network Security. This is Dr. Amr Al-Mogi. First of all, I'd like to welcome you to this lecture. In our last lecture, we started actually to discuss public key cryptography. We discussed its applications. We discussed the difference between public key cryptography and symmetric encryption. And then we went into the first public key cryptography algorithm that we will discuss in this course, which is RSA. We discussed how we can generate the public and private pair of keys using RSA, how we encrypt and decrypt, and we saw the mathematical foundations of RSA, which I hope gave us an intuition behind the design of RSA and how it can actually achieve secure encryption as well as authentication. Okay. We are going to continue the discussion of public key cryptography today. We are first going to discuss the second algorithm of public key cryptography, which is Diffie-Hellman, and then we are going to go into a new topic, which is message authentication. In this lecture, we are supposed to understand the operation of the Diffie-Hellman algorithm. Diffie-Hellman algorithm is used only for key exchange, and so by the end of this lecture, we should be able to know how to exchange a key securely between two parties using the Diffie-Hellman algorithm. And by the way, it's the one of the first public key cryptography algorithms, if not the first one that was proposed. We are going to also understand the objectives of message authentication, and we will discuss the different tools that are used for message authentication, particularly message authentication codes and hash functions. And we will study the key algorithms that are used in practice of message authentication codes and hash functions, particularly HMAC and SHA. And then we will discuss authenticated modes of encryption. Okay. So we'll start this lecture with the Diffie-Hellman key exchange. It was the first public key algorithm that was proposed in 1976. It is a practical method that is used for public exchange of a secret key. So basically, if you want to use symmetric encryption such as AES, and we know that symmetric encryption does not include a way to exchange a secret key between the sender and the receiver, then you want to use an algorithm such as Diffie-Hellman to do that. And in fact, Diffie-Hellman is the most widely used key exchange algorithm out there. There are actually different versions and different, let's say, flavors of Diffie-Hellman that are used, but they are all based on the same core algorithm that we will discuss in this lecture. For example, TLS and SSL, which are the transport layer security algorithms that are used in HTTPS, they rely on, or they support actually different versions of Diffie-Hellman. So if you establish communications with a server and you encrypt with whatever method of encryption, AES or any other algorithm, before you actually use AES in HTTPS, you have to exchange a key, and typically Diffie-Hellman is the one that is used. Okay. So Diffie-Hellman cannot actually be used to do anything else other than key exchange. It is used only for key exchange. So you cannot use it for generating a digital signature. You cannot use it for generic encryption and decryption. You can only use it for exchanging a key. In fact, mathematically speaking, the Diffie-Hellman algorithm is used to agree on a common parameter, a common number between them. And just like any other public key cryptography algorithm, such as RSA, it is based on integers and modulus arithmetic. Okay. And just like RSA, the vulnerability in Diffie-Hellman is actually known. So we know that in RSA, there is something called the factorization attack that we discussed in the last lecture. And we discussed exactly how it works. And we said that if the prime numbers are chosen to be large enough, the factorization attack becomes infeasible to be executed. In the Diffie-Hellman exchange, it's the same. The vulnerability is known, and the way to attack the algorithm is known, and it is based on computing what are called discrete logarithms. And again, if the numbers are chosen to be large enough, this becomes computationally infeasible to execute. And so let's start to take a look at the Diffie-Hellman algorithm. Just like in RSA, when we discussed RSA, the first thing that we did was to see how the keys are generated. This is exactly what we are going to start with. So the first thing in Diffie-Hellman is the key setup. First of all, the users have to agree on a global set of parameters. For example, in RSA, the users agreed on two prime numbers P and Q such that they can generate a modulus N, and then they can actually choose the public key and the private key. In Diffie-Hellman, they only choose one prime number, so a single prime number Q, and they use something called the generator A. Okay? So they agree on a prime number Q and the generator A. The prime number and the generator are public parameters. That means they're widely known. There is, however, one requirement in Diffie-Hellman is that A has to be a primitive root modulo Q. If a number is a primitive root of a prime number, that means that this number can generate all the integers from 1 to Q minus 1. So let's take as an example the prime number 7. Okay? The number 3 is a primitive root mod 7. What does this mean? It means that if we calculate 3 mod 7, 3 squared mod 7, 3 power 3 mod 7, all the way up to 3 power 6 mod 7, the result will be the numbers from 1 to 7. Okay? Sorry, from 1 to 6. That means the powers of 3 mod 7 will actually generate all the integers from 1 to Q minus 1. In this case, it's from 1 to 6. Okay? So not all the numbers are primitive roots. So 3 is a primitive root mod 7. And in fact, the number 7 has a number of primitive roots. There is no specific way to determine whether a number is a primitive root or not. You just have to figure out its powers. Now, I will continue with the Diffie-Hellman setup, and then I will explain to you why is it necessary to choose A that is a primitive root. So for now, at least we know what a primitive root is. So we choose a prime number Q, and we choose a generator A such that A is a primitive root mod Q. Given these two numbers, each device will choose its own private key XA, which can be any integer that is less than Q, any positive integer that is less than Q. Okay, so they choose the primitive number Q, the private key is XA, that is any number less than Q. Now, using the private key, you can calculate the public key using this equation. You take the generator A that the users have agreed upon, you raise it to the power of the private key XA, and you do mod Q. This is actually the public key. Okay, now this is opposite to what we did in RSA. In RSA, we did the modulus, and then we chose the public key, and from the public key, we calculated the private key. Here we do the opposite. Again, we choose the prime number and the generator A, then we choose the private key, and from the private key, we calculate the public key. Now, all the users of this system will use the same A and the same Q, but they will choose different private keys, and based on these private keys, they will have different public keys. Okay. Now, the public key, as we said, in any public key cryptography algorithm is public. That means you can actually send it to anyone, you can share it with anyone. We want actually the public key to be dependent only on the choice of the private key and, of course, the agreement of A and Q. This is actually where the property that A has to be a primitive root modulo Q becomes important. Okay, let's take an example. These two generators, A equals 2 and A equals 3. Now we know that 3 is a primitive root, modulo 7, but 2 is actually not a primitive root. Now let's see what happens if we raise the powers of 2 mod 7. So 2 mod 7 is equal to 2, 2 power 2 mod 7 is equal to 4, 2 power 3 mod 7 is equal to 1, 2 power 4 mod 7 is equal to 2, 2 power 5 mod 7 is equal to 4, 2 power 6 mod 7 is equal to 1. So you can see that generating the powers of 2 mod 7 does not result into the entire numbers from 1 to 6. Actually, the only three numbers that are generated are 2, 4, and 1. And if you keep raising the powers after that, 2 power 7, 2 power 8, 2 power 9, you will still be getting only the three numbers 2, 4, and 1. So the generator A equals 2 can only generate three numbers mod 7, which are 2, 4, and 1, nothing else. So imagine using this generator, A equals 2, in the Diffie-Hellman setup. We know that the user will generate the private key, and based on that, will calculate the public key by having A power XA mod Q. Now, if A is equal to 2 and Q is equal to 7, that means you will have 2 power XA mod 7. And we know that 2 power XA mod 7 from the table on the left will generate either 2, 4, and 1. So even if you choose XA to be less than Q, you are not guaranteed to have a unique number in the result. That means imagine one user chooses XA equals 3, and another user chooses XA equals 6. 2 power 3 mod 7 is equal to 1. 2 power 6 mod 7 is also equal to 1. That means you will have two users choosing different private keys but ending up with the same public key. This is going to be a problem. Whereas if you choose the generator A equal to 3, we can see that 3 mod 7, 3 squared mod 7, 3 power 3 mod 7, 3 power 4 mod 7, 3 power 5 mod 7, 3 power 6 mod 7 generates all the numbers from 1 to 6. Not in order, of course, but they generate all the numbers from 1 to 6. So here, if a user chooses private key XA equals 3, and another user chooses any other private key, well, 6, for example, one of them will result in public key 6, the other one will result in public key 1. Now, if you restrict XA to be less than Q, that means all the public keys will be distinct. That means all the public keys will be different. If you can choose XA to be greater than or equal to Q, you will start to have repeated public keys. You will start actually to have the same problem once more. Okay, this is why we choose the generator to be a primitive root modulo Q. Now, let's see how the Diffie-Hellman exchange actually works. Let's say you have these two users, A and B. They have agreed on a generator A that is a primitive root modulo a prime number that they also agree upon Q. A chooses its private key XA, B chooses its private key XB. Okay, both of them have to be less than Q. Now A calculates its public key YA equals A power XA mod Q. B calculates its public key YB equal to A power XB mod Q. Now, as we said, the goal of the Diffie-Hellman exchange is to establish a secret key between two users. So now we assume that A and B want to actually exchange a secret key between them. What they do is that they send to each other the values of their public keys. So YA is sent from A to B, YB is sent from B to A. So now A has YB and B has YA. Now note that they send only the public key. That means the result of the exponentiation A power XA mod Q and the result of the exponentiation A power XB mod Q. They don't actually send XB and XA, only the exponentiation. And so someone can say, well, given the value of the public key and the fact that I already know A and Q, can't I just actually figure out the private key? Well, yes, this is where the vulnerability that we discussed becomes actually apparent. To compute XB from YB, you have to take something called the discrete log. Okay? If XB, A and Q are small numbers, then actually computing the discrete log is an easy matter. If they are chosen to be large numbers, then this becomes computationally infeasible. Same as with the RSA algorithm. If the values of the prime number P and Q are small, then factorizing the modulus n will be an easy task. If you choose them to be large numbers, then factorizing n will be a computationally infeasible task. Okay. So again, here, even though you know the public key and you know A and Q, computing the discrete log should be a computationally infeasible task if you choose numbers that are large enough. Okay, so how can they calculate the secret key given that they have exchanged the public keys with each other? Very simply, A will take YB and raise it to the power of XA mod Q. B will take YA, the public key of A that has been sent to it by A, raise it to the power of XB mod Q. What does this result in? What is actually the value of YB? YB is A power XB, and you raise it to the power of XA mod Q. Same thing on the other side. YA is equal to A power XA. You raise it to the power of XB mod Q. Now take a look at these two expressions. They are equivalent. So both of them calculate the exact same number, which is the key that is exchanged between A and B. Okay. So the value that they calculate as a result of raising the public keys to the exponent of their private keys is actually the exchanged key. Note here that they both were able to calculate the exact same value KAB without sending to each other their private keys. They only have to send to each other their public key. And without having a centralized device between them, without having a key distribution center, they can actually exchange the key securely among each other without actually having any trusted third party. So the only thing they have to do is actually trust each other. And in the web, you don't actually trust the server, but if they have a security certificate, that gives you some authentication information about it. Okay, so this is how the Diffie-Hellman exchange works. So here KAB is equal to A power XA XB mod Q, which is equal to the public key of A to the power of the private key of B, or it is equal to the public key of B raised to the power the private key of A mod Q. So B can compute this one because it has the public key of A and its own private key XB. A can compute this one because it has the public key of B and it raises it to the power of its own private key. Okay, so both parties choose their own private key securely and they don't exchange the private key with anyone. Okay, and they calculate the public key and exchange it with each other and use that to calculate the shared key. Okay, now this is a numerical example. Assume that Alice and Bob wish to swap keys. They agree on the prime number 353 and the generator A is equal to 3. Now they select two random secret keys. A chooses the private key 97, which is less than Q, obviously. B chooses the private key 233, which is also less than Q. Now they both calculate their public keys. A calculates its public key by raising the generator 3 to the exponent of 97 mod Q, which is 353. The result is 40. YB is equal to 3 to the power of 233 mod Q, or 353. The result is 248. Now, if you try to put these numbers, 3 power 97 and 3 to the power 233 on a calculator, you will not get a result. So you have to do the square and multiply. You have to do, for example, 3 power 3 mod Q multiplied by 3 power 3 mod Q, and you keep repeating that until you reach 97, and same thing for 3 to the power 233. Actually, if you calculate 3 to the power 97, which is 40, you can use that result to calculate 3 to the power 233. That is, if you get this problem in an exam, obviously. Okay, and then they can actually calculate the shared key. Okay, so to calculate the shared key at A, you have to have the public key of B. So B, or Bob, sends it its public key, and A raises it to the power of its private key. So it's YB to the power of XA mod 353. So YB is 248 to the power of the private key of A, which is 97. Mod 353 is equal to 160. If you take YA to the power of XB, or 40 to the power of 233 mod 353, you get also 160. So you see how both Alice and Bob end up actually sharing the exact same secret key. All right. Unfortunately, the Diffie-Hellman exchange is vulnerable to a very well-known attack, which is called the man-in-the-middle attack. And I want you here to pause the video and think about how this attack can actually be executed. Basically, the attacker will place himself or herself in the middle between Alice and Bob, and by fooling Alice and Bob, the attacker will end up exchanging a secret key with both Alice and Bob, instead of Alice and Bob actually exchange secret keys with each other. Pause the video, think about it, and then play to get the result. Okay, so now we have our three components. We have A, we have B, Alice and Bob, okay, and we have the attacker E in the middle. So Alice and Bob think that they have actually agreed on the generator A and the prime number Q, okay, and these are public numbers, so the attacker would know them as well. A chooses XA, B chooses XB, A uses XA to compute YA, B uses XB to compute YB, and they send it to each other. Now let's say the public keys are intercepted at the attacker. Okay, so the attacker intercepts the public keys YA and YB. What can the attacker actually do? The attacker can simply have or choose a private key to be exchanged with Alice and a private key for an exchange with Bob, and then calculate the public key of that private key and the public key of the other private key. Okay. So now, when the attacker intercepts YA, it will use YA to and raises it to the power of the public key or of the private key that it has chosen for itself. And when it receives YB, it will use YB to raise it to the power of the private key that it has chosen for the exchange with Bob. The result that it will send its public key YEA to Alice, and it will send the public key YEB to Bob. And so Alice will think that this public key came from Bob, and Bob will think that this public key came from Alice, whereas they actually came from the attacker. So using this exchange, the attacker will effectively exchange a key with Bob, and using this exchange, the attacker will effectively exchange a key with Bob. So a key with Alice and a key with Bob. So now effectively the attacker has actually exchanged two keys, one with Alice and one with Bob, and Alice and Bob will not know that this has happened. This is called the man-in-the-middle attack. It's a very well-known attack on the Diffie-Hellman algorithm. Now, what is actually the cause of this attack? Why was this attack successful? It was successful because the public keys that were sent by any device, YA, YB, and indeed the public keys that were generated and sent by the attacker are not authenticated. So if I send a public key, I'm sending a value. No one knows where this value came from. And so indeed an attacker can generate the same value or a similar value and claim that it came from another device. And so fooling another device that this value came from Alice or came from Bob. And so Alice and Bob will be fooled. So what is the solution to that? There are actually forms of Diffie-Hellman that are called authenticated Diffie-Hellman. Okay. One way to have authenticated Diffie-Hellman is to send a certificate, a security certificate such as the one that we discussed in the last lecture, with the public key. And we know that the job of the security certificate is to uniquely identify a user. In fact, the security certificate, what it does is that it binds the identity of a user to their public key. If you open last time's lecture, you will find in the example of the security certificate that one of the entries is the ID of the user or the one that obtains this certificate, and another entry is their public key. This is exactly what the security certificate does. It binds the identity of the user to their public key. And so if you want to have authenticated Diffie-Hellman, each user can have a security certificate that binds their identity to their public key. And the certificate will be generated by a certificate authority and can be authenticated easily. And so if this happens, it will be difficult for an attacker to claim that they are an alternative user because they will not have the security certificate of that user and they cannot be authenticated. Okay. This ends our discussion of the Diffie-Hellman algorithm. And for the remainder of this lecture and for the next lecture, we are now going to actually move into another topic, which is the topic of message authentication. It is actually a very important topic in security, and it is concerned with three main objectives: protecting the integrity of a message, validating the identity of the originator, and non-repudiation of origin, which is dispute resolution. What does it mean? If I say that a message is authenticated, that means I want to protect the integrity of this message. That means when the message is sent from sender to the receiver has to be able to verify the contents. That means the receiver has to be able to verify that an attacker did not manipulate the contents between the sender and the receiver while the message was on its way. It means also that the receiver is able to verify that the message came from the user who claims to have sent it. This is validating the identity of the originator. So when I receive a message, I verify its contents and I verify where the message came from. And the final objective is non-repudiation, which means that the sender cannot later deny sending a message. This is used for dispute resolution. If the sender and the receiver are having an argument, and one of them is claiming not to have sent the message, non-repudiation should actually guarantee that this cannot happen. Okay, you have to be careful here that this is the first form of authentication that we will discuss, which is message authentication. Later in the course, we will discuss user authentication. There is a unique difference between the two. Message authentication is concerned with the three objectives that you see on the slide. So it has nothing to do with authenticating the user himself or herself. So I'm not trying to actually validate the identity of a user. I'm trying to validate the contents of the message and the origin of the message. Later on in the course, we will discuss user authentication in details, which allows a receiver to verify the identity of a user, identify where who the user is basically, rather than having anything concerned with the message itself. All right. Now, before we go into the details of message authentication, let's review quickly the security requirements that we have discussed before in this course. And to do that, we will discuss actually the attacks that are possible on a message that is communicated between a sender and the receiver. We'll start with disclosure. Disclosure means that an attacker is able to reveal the contents of a message on its way from sender to the receiver. To do that, the attacker, for example, can break the encryption of a message or something like that. So, usually to protect against disclosure, we use a strong encryption system, such as AES with a large key, for example. If you use that, then you are protected against disclosure. The second requirement is called traffic analysis. Even if you encrypt a message, you are still vulnerable to traffic analysis because an attacker can still infer a lot of information about your communication. The attacker can learn to whom are you sending and how often are you communicating with that person, and when do you usually communicate with that person, and what is actually the pattern of communicating with that person or with that entity. Traffic analysis can reveal a lot of information that can be just as disruptive as information disclosure itself. The first two security requirements that are discussed, disclosure and traffic analysis, are dealt with using some or the other forms of encryption. Then you have something called masquerade. Masquerade is basically an attacker pretending to be another person in the system to gain access to the system on their behalf. So you send, for example, a username and password on behalf of a user to claim that you are that user so that you gain access as if you are them. Okay? Then you have content modification. Content modification means that you have a message that is sent from sender to the receiver and you manipulate its content. You change some bits from zeros to ones or ones to zeros, for example. Then you have sequence modification, meaning that you don't actually change the content of a message, but you change their sequence. You take the first message, you put it in the end, you take the second message, you put it first, and so on. Now, sequence modification, its problem is that if the order of the messages is important, then you will be able to fool the receiver into doing something that is not supposed to happen. And after that, we have something called timing modification. Timing modification is that, for example, you delay the arrival of certain messages. This is specifically important if the time at which a message is received is crucial. Later on, when we will discuss key distribution and user authentication, we will know that there is something called a timestamp. If a message is received after a timestamp expires, the receiver has to throw it away. And so timing modification can actually have something to do with that. All the requirements that you see in green, from masquerade, content modification, sequence modification to timing modification, all of those are the realm of message authentication. This is what message authentication deals with. These are the attacks that message authentication are concerned with. Finally, we have source repudiation and destination repudiation. Source repudiation means that the source is not able to deny sending a message, and destination repudiation implies that the destination is not able to deny receiving a message. Both of them are based on some form of digital signatures. Destination repudiation is also based on a digital signature, but it also relies on feedback. So if you want destination repudiation, after the destination receives the packet, it has to reply with a digitally signed acknowledgement saying that I have received this packet, and because the acknowledgement is digitally signed, the receiver cannot later deny actually receiving the message. Okay, these two are the area of digital signatures, which we will discuss also in details later in this course. Actually, we'll discuss them when we discuss blockchains. Okay, so we now go into message authentication. Message authentication is typically done based on something called an authenticator. Now, keep in mind that we are doing message authentication so that we are able to protect the integrity of a message. We are able to protect the content of a message that are sent from sender to receiver. Basically, we want to protect against content modification and sequence modification. We protect against sequence modification by simply inserting a sequence number in the packet. And if we are protecting the integrity of the packet, then we are protecting the sequence number as well. And the authenticator is also able to protect the identity of the originator, meaning that I can validate the identity of the originator, and this protects against a masquerade attack as well. Now, message authentication typically happens using one of two forms, either a message authentication code or a hash function. But before we discuss what is a message authentication code and what is a hash function, let us first see whether our regular message encryption is able to do message authentication by itself or not. Because if we decide that it can, then we do not actually have to do anything else. Our job is done. So let us first see whether message encryption is able to do the job or not. Okay. Message encryption is done either using symmetric encryption or public key cryptography. So if we're using symmetric encryption, then we know that basically we have the plain text P that is passed through the encryption algorithm together with the key K. Out comes the ciphertext C. This goes to the receiver. This is the encryption algorithm. This is the decryption algorithm. So the ciphertext with the key are passed to the decryption algorithm. Out comes the plain text back. So we want to see whether this system on its own is able to protect the integrity of a message and validate the identity of the originator. Since the key is shared only between the sender and the receiver, then the receiver can actually know that the message came from the sender because no one else will have the key. So symmetric encryption can indeed protect or validate the identity of the originator. Now, note here that we didn't say that this does non-repudiation. Non-repudiation has to depend on a unique key. It has to depend on a private key, actually. So this system, the symmetric encryption system, allows you to validate the identity of the originator because it is the receiver who wishes to validate. But it doesn't do non-repudiation because the receiver can still claim that the message came from the sender because the receiver also has the key. So you have to just differentiate between these two things. Digital signature or non-repudiation can only be achieved using public key cryptography or encrypting with a private key. Okay? Okay, so symmetric encryption can validate the identity of the originator. Can it then protect the integrity of the message? In the ciphertext message that is sent from sender to the receiver, is the attacker allowed to manipulate the bits, changing zeros to ones and ones to zeros, without the receiver actually figuring out that this happened? Well, this depends. If the message has a deterministic structure, meaning that it is in the English language or something like that, and the attacker changed zeros to ones and ones to zeros, the result or the resulting plain text will have a weird structure that the receiver will not be able to detect. And so if the message has a suitable structure, then yes, symmetric encryption may be able to detect whether an attack on integrity has happened between sender and the receiver. But if you're just transmitting a sequence of bits, as typically happens, because usually a large message is divided into blocks, then you will not actually be able to detect that this has happened because the message may very well not have a suitable structure or a deterministic structure. And so symmetric encryption by itself is not a very practical way to do message authentication, because even though you can validate the identity of the originator, you are unable to fully protect the integrity of a message. If we look at public key cryptography, we find that it is more or less the same. If we encrypt with the private key of a user, not only do we validate the identity of the originator, we also achieve non-repudiation in this case, because it is a unique key. However, it has the same problem with the integrity. If an attacker changes ones to zeros or zeros to ones, and the message doesn't have a deterministic structure, the receiver will not be able to detect that an attack has occurred. This is why we don't actually rely on symmetric encryption or public key cryptography on their own to do message authentication. We rely, as we said, on two things: something called the message authentication code, and something called the hash function. And sometimes hash functions are used actually to generate message authentication codes. In both MACs, or message authentication codes, and hash functions, we use them to generate something called an authenticator. And then authenticator is an extra piece of data that is concatenated with the message and sent with the message from sender to receiver for the receiver to be able to validate the contents. Okay, so the MAC is basically a small fixed size block of data that depends on the message and some key. However, it need not be reversible. So a message authentication code is generated using an algorithm. You give it the message and you give it a key. It's a symmetric key. And out comes a message authentication code, which is a small fixed size block. So even though the size of the plaintext message may be variable, the output, which is the MAC, is a fixed size block that is a function of the message itself and the function as well of the key. Unlike symmetric encryption, message authentication codes or message authentication algorithms need not be reversible, because you will not actually reverse the encryption. Here is actually the operation. It is shown in the figure below. You take the message, you give it to the MAC algorithm together with a symmetric key that has to be exchanged between the sender and the receiver. You generate here the message authentication code, and you concatenate it with the message and you send both to the receiver. So the receiver receives the message and receives the message authentication code that was generated using a particular key. How can the receiver actually use it to validate the authentication of the message? The receiver basically repeats the process. The receiver takes the message part and uses it to generate the exact same message authentication code with the exact same key. And the generated MAC is used to compare with the MAC that was sent with the message. If the two match, then this message must have been used to generate this MAC using the same key. It is actually the only way that this could happen. The same message was used to generate the same MAC using the same key. So this means that the message was not manipulated on its way, because if it were manipulated on its way, the generated MAC at the destination will not match. And it also means that the originator is now validated, because I will not actually be able to verify the MAC unless I have the same key as the sender. Okay, so this provides assurance that the message is unaltered and comes from the sender. There is, however, a very important thing to note here. The message may have a variable size. If it is passed to the message authentication code together with the key, it produces a fixed size block. If the message has size n, let's say actually the message has a fixed size n, and the message authentication code has a fixed size b. Typically, b is much less than n. Okay, so the size of the message authentication code is typically much smaller than the size of the message. Otherwise, it would not actually make sense. You cannot generate a very large block of data just to be able to authenticate the message. This is not practical. So the size of the message authentication code block that is generated has to be much smaller than the size of the message itself. Okay. What does this mean? that the size of the MAC is smaller than the size of the message. It means that this is not a one-to-one mapping. There is probably more than one message that will result in the same MAC. Because if the message has fixed size n, how many possible combinations do we have of the message? We have 2 power n. And if the MAC has a fixed size b, then this means we have 2 power b possible message authentication codes. If 2 power n is greater than 2 power b, okay, what does this mean? It means that the mapping is not one-to-one. It means that there is more than one combination of a message that will lead to the same MAC. In fact, there are 2 power b over n possible combinations that will result in the same MAC. Okay? If you have 2 messages or more resulting in the same MAC, this is called a collision. A collision is when you have more than one message resulting in the same MAC. So, technically speaking, an attacker can find another message that has the same MAC. And if the attacker is able to find that message that has the same MAC, the attacker can simply replace the message M with M dash that has the same MAC, and this will be correctly validated as the receiver because it will have the same MAC. Okay? However, just like any cryptography algorithm, this should be computationally infeasible to find. So here we now arrive at the requirements of a message authentication code. The message authentication code has to be designed such that it is infeasible for an attacker to find an alternative message block that has the same code. In other words, it is infeasible for an attacker to find a collision in the message. Okay? Even though we are 100% sure that collisions exist, it's just by pure math. It should be infeasible for an attacker to find such collisions. And it is indeed infeasible in efficient message authentication code algorithms. Okay. One thing to note is that in the figure below, we have generated the message authentication code. We have achieved integrity and authentication. So we have validated the identity of the origin, and we have protected the integrity of the message, given, of course, that it is infeasible to find a collision. This, however, does not achieve confidentiality. Because you see here, the message is sent in the clear. The message authentication code is the one that is encrypted using the message authentication algorithm and using K. But the message itself has not been encrypted. You generate it and you send it in the clear. So this setup here by itself does not achieve confidentiality, only integrity and authentication. This figure here shows you different combinations achieving actually different objectives. This is the first one that we just discussed. Now, if you want confidentiality in addition to authentication and integrity, then you have to add a second layer of encryption after the concatenation. So basically here, you generate the message, you pass it to the message authentication code with the first key, K1, you concatenate both, and then you pass both to a second layer of encryption using K2. Okay. Now, using different keys for message authentication codes and encryption is not mandatory. You can actually use the same key, but it is a security recommendation to have different keys, and this is typically what happens. Now, at the receiver, if you do that, what is done? You actually do the same steps, but in reverse. So because the last step was the encryption with K2, the first step at the receiver would be decryption with K2. Okay? And then you have the message with the message authentication code. So you validate in the same way. You take the message, you pass it to the exact same message authentication code algorithm with the same key K1, and you generate a MAC, and you compare it with the MAC that was sent along with the message from the sender. If they match, then the message is validated. So the first one, as we said, achieves integrity and authentication. The second one achieves also integrity, authentication, because there is a MAC, and it achieves also confidentiality. Okay, so the three requirements are actually achieved. Notice here that this doesn't achieve non-repudiation. As we said, non-repudiation can only be achieved if you use public key cryptography. Now, These keys that are used here, K1 and K2, are symmetric keys. And so message authentication code is typically generated using a symmetric key. Okay. Now, the problem with the symmetric key is that it is shared between the sender and the receiver, and the receiver may claim that the message actually came from the sender. The third one that we have here is that if you flip the order of encryption, so first you have the message, you encrypt it with K2, and then you take the encrypted message and you use it to generate a message authentication code. In this case, the message authentication code is not generated for the message, but generated for the encrypted message. Okay. So after that, you concatenate both the encrypted message and its MAC, and you send both to the receiver. Now here, because you did the message authentication code last, the verification now has to come first. So now you take the message authentication code that was sent, you take the encrypted message here, you pass it to the message authentication code along with A1, and you take the attached MAC and you compare them. If they match, then the encrypted message has been validated, and then you can take the encrypted message and decrypt it with K2 to obtain the plain text. Now, whether you do the encryption with K2 first, as in the third example, or second, as in the second example, that depends on your application. It depends on who gets access to what. If you don't want to give the validation function access to the content of the message, then you use the third mode, meaning that you have, for example, a third-party algorithm that does the test on validation, okay, that does the test on integrity. And you don't want to have it read the content of a message. So you just give it the encrypted message. It doesn't have to. So it can validate the content of the message without actually reading the contents of this message. Whereas if it doesn't matter to you whether the content of the message are revealed to the validation algorithm or not, then you can just actually use the second way. There is no external complexity. There is no drawbacks here. It just depends on what you're trying to do. And the second one achieves the security requirements as the third one. So this one achieves integrity, authentication, and confidentiality, and also does not achieve non-repudiation. Okay, because it's also based on symmetric keys. All right, we'll stop here today, and we will continue our discussion of message authentication codes next time.